then we have a simple optical system where we have an objective coupling out to spectrometers. We can take spectra as data set and as imaging, and we collect like source in the fiber. This is two data sets, one black one after, before initial stretching of the fiber, and the red one after 100 times stretching and releasing to 100% strength. And you see that they behave very robust at 100 times. So now we're running more careful experiments. We want to go to several thousand cycles to just see what happens if it's time to perform within this reversible range that we think is up to 100% strength. So that should work. We should be able to show how durable and how pertinent the strength they are, or exposure to strength. The other thing that we're trying is to go away from 10 centimeters and go more to something on the meters and maybe the kilometers range, which is really big. And that is obviously difficult because it's a linear process. You're rolling these fibers, and so you roll the cladding onto the core, and then you can imagine being slow. The approach that we take there at the moment is that if we can make films that are larger than 6 inches that we call the wafers at the moment, in the semi-infinite process, then we can pick up this film with a fiber that's translating as we rotate. And so you can imagine it's like a bandage that you roll at an angle around the leg, you can cover the whole leg. The angle will decide how many multilayers we get, and if you translate the fiber at some speed, we should be able to create larger amounts of fiber width than the width of the initial polymer. So what we're trying to do is, and that seems to work rather well, I dare saying at this point, is creating polymer films on one end on the wall surface, flowing them down to where we roll them up, and here you see the two different materials coming from either side. And so the polymer is liquid here with the solution, forms the film as the solution operates, and then we pick that film up on this side onto the fiber. This is a prototype setup, seems to work well, but now we build a translation setup that we can also move the fiber along as we go. And that hopefully give us a handle to scaling this material. And that is the limit of what my lab could do for this. And then I want to convince companies like 300 to take from this and build this on larger scale. There's one more challenge in that, and that is that the cladding is the outside of the fibers at the moment. And if you rub a fingernail or razor blade along that, you take the cladding off and you take the color off. And so what we're doing at the moment is we're trying to get about 10 micrometers thick layer onto that. That will be transparent and that will protect these multilayers from mechanical damage. And so I think there's good way of doing that, or else this makes it worse. Alright. I'm going to switch gears on that one here. I talked a lot about fibers. I want to talk about a biological system from which we gain some inspiration for something different. I'm going to focus mainly on the biological system. That would be this limpet here. We haven't actually used some of the insights in our field system yet, but I think that's some interesting things that we could. Let's work then together with Christina Thies and Joanna Eisberg at Material Science, MIT, and the School of Engineering and Applied Sciences at Harvard. And one of the people linked here, for example, is incredibly good with structural analysis of materials. You can do anything that's focused ion beam, scanning electron microscopy, transmitted electron microscopy, better than anyone I know, essentially. So I was very lucky to find him to work with us. And Natalie, at the moment, I'll show you in a second, my student in my own lab, she is growing live limpets now, and we're doing experiments with these limpets. I'll talk about this. Alright, what's interesting about those guys? First of all, they're tiny, so they're easy to handle, and we can study them. The second one is they have these transparent shells. And these shells have these blue and bright features in the translucent calcium carbonate shell. And we were interested in what makes these blue features. And initially we started out as having this as a pet project, if you want, because my brother, marine biologist, just found them, and he brought them along the lab, and we looked at them because we were interested in colors. It turned out to become a lot more. And what we saw initially was that when you look at these structures in reflection, they're blue. In transmission, you see a different color, darkish red. When you put them in water, they change color a little bit if you have a damaged stripe. So that means that there's some fluid that goes into something, displaces the air. And when you take it into a stereo microscope, you light it from the top, you have from the top, and rotate the sample. Now we see the outside. You find that these stripes lighten up and then they're down again, depending on the orientation of these stripes. And that is a strong indication that it can't be a pigment, but it has to be something that's of a structural nature. When we try figuring out what the structure is, the initial thought is maybe it's a surface. So you look at two surfaces and we didn't find anything. Nothing on top, nothing at the bottom, the interior of the shell. So it had to be on the inside. So on the following slide, I'll show you how we go about to revealing that secret. You have to look on the left side and you see the artistic rendering of the techniques that we use. And then on the right side you see the different images at different scales that we obtain. So for example here is an X-ray tomography image and you see the locations of the stripes being slightly different. And then with microscopy, scanning microscopy, we can see small features in the interior of the shell. And we use focus ion beam to cut a small lamella out of the cross-section of the shell, and then you can see the high resolution structure of the limpets morphology that is at the origin of the blue color. The blue, as you can see here, in this area here, is from the multilayer. There is other stuff underneath this. So this all the areas of particles that we found very interesting. Multilayer is something that is pretty often found in nature, so it wasn't that interesting, except maybe for the point that's in calcium carbonate. So there wasn't a organism known before we started this study that used calcium carbonate lamella for displaying a feature that's very likely having an optical purpose. Similar structures, however, have been found in nacre, and that's where you see the pearlescence of the inside of the nacre shell. But that's an artifact, in my opinion, of the mechanical process of these structures. So what's interesting is multilayer factor. That's more interesting from its material composition. Calcium carbonate outside, it's monocrystalline. So throughout the most likely you have one crystallization and it's a little bit birefringent. So you get some polarization effects as well. You haven't fully characterized this to an extent that confidence speaking of it, not to understand yet. The particles underneath were something that I hadn't seen before. And what's interesting is that they're always localized with multilayer. So the multilayer is localized in small areas in the shell and also the stripe. And particles are localized underneath that multilayer of calcium carbonate. What you see here is a cross section. It's a reconstruction, topographic reconstruction that we take from synchrophonator that we obtained at the advanced photo source international labs. So we cut a small section of the calcium carbonate shell with focus ion beam, and we mount this on needle, take this to the argon labs and get the whole three-dimensional structure. And that means we can do better optical simulation with this, for example, in terms of optic properties, the stripes are interesting from the point of view that they have these regular correlations. And what you get from that is when you look at this in a microscope, and you put next to the lens, the vertical lens, we don't know how it does. If we don't image real space, we don't image just the surface of the sample, but we put a lens in that images back focal plane of the objective, we can essentially get information about the direction in which light propagates from our sample. So the images that we get from that are shown here, one of them. You read this in a way that you look at the center of the image, and that will explain you how light propagates particular from the shell or from the sample. So the center of the image is light that comes out directly normal to the surface of the structure you look at. And as you go further and further from the center of the image, the exit angle from the structure will be more and more inclined to the surface. And then when you go around the circle here, there will just be different orientations of it and a bit of a certain inclination. So we get information about how an optical structure scatters light if we look at the back focal plane of the objective or just one Fourier space viewport. For diffraction grading, we will see essentially diffraction pattern. What's interesting about limpet is that the correlations here match very well with where we see the maximum reflection in the blue here. So it has these sort of interesting reflection patterns. We just shown it has to be as a function of angle of light exit. And that explains essentially why you've seen these stripes lighting up and dimming down again, because as you rotate the limpet shells through, you might observe here that you're going to see that light flashing up and down again. It makes it very apparent if you dive and you happen to see them in the kelp forest relative, they flash bright blue flashes. And my brother tells me you can see them up to 5 meters distance. Now mind that they're only like fingernail size. So it's a pretty strong optical signal if you have enough light. The particle is a bit more interesting. At the beginning I didn't know what I was looking at, and I was thinking they would create a lot of scattering and maybe then make sure that light that transmits through the multilayer reflector doesn't come back and give you a reflected spectrum. It could also be absorption, so at the beginning we weren't very clear what it is. We were biased towards scattering because we've seen that there's a lot of calcium carbonate in these particles, and that doesn't have any intrinsic absorption. But when you take an optical microscope and you just look at it with an oil immersion lens, very high magnification or very high resolution, say, you see these emission particles, and you can see how the intensity drops of reflection and transmission as a function of the number of particles. And that is obvious when you see the image. Particles are not necessarily round. There's a lot of internal structure, and that's sort of interesting for calcium carbonate because it always wants to form crystals. That doesn't seem very crystalline. They actually turn out to be amorphous. And so there's something in there that stabilizes the amorphous phase. I still don't know exactly what, but I'll tell you in a second what I think it is. That doesn't help us understand what they're really doing. For really understanding what they're doing, we finally found a little trick after quite some time, and that was painting the interior of the shell white. It's not quite obvious why the trick would work and tell us if these particles are scattering or absorbing, but I show you that it actually gives us all the answers we want to have. When you look at the stripe and reflection, you essentially only see the light that's reflected from the multilayer. Anything that passes through that's complementary color, you can't catch. And you don't know what's happening here. It could be scattering, or it could be absorbing. It's not really clear. You can look at this in transmission, and you see where the particles are for these dark areas. And then you also see areas where there's no particles, and you see the red light just transmitting through. So where there's particles, light gets attenuated. Where there's no particles, light can travel through and see it's actually. When we now take an area where we painted the underside of the shell white, what you can see is that where there's no particles, almost no color is retained. And that's the area here, and then the area here. So it's very pale. And the reason why that is that you reflect light from the multilayer, and then you scatter light from the underneath white surface, and the complementary color, and you add them up again, and you get a very sort of non-biased spectrum. So it's very pale. So what you see in the other areas of particles are is that the red light that gets through doesn't make it to the white scattering layer underneath. And that means that there has to be absorption. Because if that would just be a scattering layer that would behave like white underneath, it would essentially have the same effect as white or green. And so I think that was a pretty neat way of showing with very intuitive means and very low-tech components that particles are absorbing. What they do here is they provide backdrop for and then erase essentially the complementary colors that are not blue, so that you don't get the spectrum depurified with these colors that you might want. So it's a combination of a filter and an absorber, and you find this in many different sort of biological structures that rely on the structure of color. It's often that you combine a material that's kind of transparent and has a structure so that you get light interference and color from that, with absorbers and right positions to clean out your spectrum in color ranges that you don't want to have. Now, I think we understand the optics, and we also understand a lot about the materials. I can tell you more about the materials if you're interested in that, and discuss this in great detail here. We don't necessarily know the purpose of it. It's an interesting question to ask. This is almost a question that's impossible to answer, but we gave it a bit of a shot and speculated a little bit. We think it has an optical purpose. And the reason why we think that is because the reflection maximum of these structures is coinciding with the absorption minimum of seawater. So it's sort of the color blue that you want to signal something in underwater if you want to signal something vision. And you can see that when you correlate the reflective spectrum with the spectrum of light that you get at different water depths. Here at 0 meter water depth, we see essentially the sun spectrum at 0 meter water depth on our Earth. As you go down to 5 meters, 10 meters, you see how the spectrum gets depleted of reds and yellows and greens. And we have, for comparison, the activity of the limpet structure in these different spectral environments. You can see that the color doesn't change much, and even the intensity is pretty stable down to 10. This happens with between 0 and 15 meters. So it's very nice for maintaining, if you want, a recognizable signal. You have very good continuity because the signal doesn't change throughout the water column. So the signal is the same thing everywhere. Those limpets happen to live in groups on kelp, but they do a funny thing. These kelp plants that they're also eating are very exposed visually, so there's large flat leaves that you can see very well in the water. And the organisms that live on these large flat leaves, the limpets, they make these thin blue stripes, and they also make a relatively thin shell. there is a second kind of them, same species, but it changes its sort of appearance when it decides to migrate down to the holdfast in areas that are very concealed. Very little light environment there as well. When it's going there, I'm not sure what makes it decide to go here or there, but when it's doing that, it's starting to make these blue stripes. You can see just about appearing here, and it's rather making a very thick shell. It's also starting to overgrow all sorts of stuff, and this one doesn't. So the takeaway here is, if it's highly visually exposed, it's making blue stripes. It doesn't care about making a thick shell. If it's hidden away in these holdfasts, where it can only be seen once you're already sitting on it, it's rather making it very thick. And so what we think is this is for photonic predation. And photonic predation with the color patterns potentially because it's mimicking something in its immediate environment that is known to be poisonous to most predators. These are these nudibranches. They have these interesting blue features on soft bodies. So they're very soft, liquid creatures and but they have these bright blue features to advertise that they're not palatable, that they're poisonous. So what we think is the limpet in these either individually or in these groups is mimicking these poisonous nymphs to actually hit your light and can poisonous even without making poison. And so the one that's hidden beneath the holdfast is only in because it's only going to be seen once predators right on it. Right? So there's one more thing that we're not trying to do with limpets, and that is understanding how it's actually making the structure. It's a very interesting organism because it's tiny, the shell is relatively flat, so you can access it optically. But the main important reason why you can access it is that at the inner side of the shell, you have a growth edge that you can make all different structures appear at different points in time. So if you look at this growth edge, and this is the optical microscope image, and this is the corresponding scanning vector microscope image, you can see in different areas different stages of formation of these structures. And so we can start to see mobile transparent lamella of calcium carbonate. You can see the multilayers, and this is a projection of them, and you can see the particles. And so what we're trying now to do is we're trying to culture these organisms. And so far we have been pretty successful since October with maintaining them. We haven't cultured yet, they haven't reproduced, but we can at least maintain them. And then the question is, can we look at these under the microscope at different ramifications and and reveal what's forming the stripes in terms of the mantle and the organics only, and how is it formed. And so these are very initial pictures that we took at different points during the morphogenesis of the limpet. And these are 3 consecutive days at the same position with 6x all immersion objective. And they're not perfect. So these images don't show us perfect. But I think we can go a lot further by optimizing image conditions. We reconstruct these images because the shells are curved. So we have to optimize the construction algorithm. And maybe we can actually start to see phenomenologically how these structures form and visualize it over the course of several days, weeks, and months. And then maybe we can start tinkering with the material. Or even use other techniques like AFM to very locally look at what this organism does. And it's again not a bad model system because it's relatively planar and accessible to the AFM potential. Alright, so I think that brings me to the finish of the talk. And there's 2 remarks that I will make. One of them is that it's interesting to see in nature that there's organisms that have come up with very unconventional solutions for optics, using materials that we wouldn't necessarily recognize as good optical materials. Putting them in a shape and in a context where they actually perform very well. And it's funnily enough the smaller things, the limpets, for example, or insects, that can teach us a whole lot about optics to a certain extent. At least robust optics, maybe not best in high quality factor cavities, but robust into optics for visual fields. And the other thing in fibers, we can take as much or as little inspiration as we want from some nature organisms. There's one good thing about it, nature will never sue us for copyright infringements. And we can always take the knowledge we get from nature systems into contexts that we know, different material systems, different theoretical backgrounds, and see if we learn something from these nature systems. So they may form an interesting starting point is my group of grad students at the moment, undergrad students. They're all pretty amazing. I have all different projects, and it seems like most of these projects are actually going to bear fruits. A couple of physics students that have been spending some time in our lab that were incremental to getting this out this stuff. And then the two projects that I showed you relied on the input and help from a lot of different students and also faculty and postdocs. That are shown here. Link is the person that I already mentioned that has done a lot of this limpets actually. He does amazing work there. Brother Fadi always. And Laura and Tim are working on tunable optics, and they have really made materials for us to play with. And then Afi and Pete, for example, were involved in the work with fibers. And here, for example, here are Joanna and Uli that were two of the most important mentors in my PhD time and my postdoc time, who worked on vertical science. All right, we got some money from different sources. I definitely have to get more to maintain my students happily and healthy. And we'll slowly do that. And thank you very much. That is traditional for the questions or for the
just curious about the first stretching fiber and then the color change. So what will going on if you keep stretching it? Like after blue, after purple, what will show?
So there's two things that could happen. After purple, you would go in infrared. It's just a move.
Yeah.
The only problem is that I think beyond 50%, you start to behave to hit the fibers elastic limits, and so they start to essentially shed their cladding. Cladding starts to break areas of fracture. We can stretch these fibers up to 300%, and then there's some plastic behavior of cladding. The cladding might start to slip. We don't know fully yet what's happening. But essentially it breaks. So it doesn't perform the same way, and we get a lot of scattering once we then bring it back to original. So the cores per se are capable of deforming 10 times the original length, but the cladding doesn't come to it. We might be able to mitigate that with different materials. We use PDMS at the moment. I think that's the silver 184 component. That's limited in its extension. But there's other materials that you could put in place.
On the football helmet application, you would kind of want a limit recording. Are you doing anything to kind of recording the history of the strain?
So that was our hope with the internal structures. So the external ones would really be purely for the referee to see if somebody was really hit very hard, and maybe for the players to brand and hit somebody hard if they see that it's right. But the internal structure would have been a layer that would have been essentially an optical sensor that relies on the instantaneous information of these structures, and then we convert that information into an electron signal with the intensity read of and send this via wireless communicator to our field computer view. So then we could get this history of effects, because in the NFL's project called, they also wanted to have sort of a history of small scale effects that could lead to concussion decimation. That was that answer your question?
Yeah, that's right. Or have you thought about embedding the fibers in a plastic material which doesn't restore? That's non-restore.
Restores on different times there.
Right, restores at a very slow.
Ultimately, you want to restore because it has to last for several different effects.
Right.
Yeah, so that's definitely something we discussed. How do you get this plastic or viscoelastic component, let's say, to fibers, and we get it in the surrounding medium? Claddings are a pretty huge structure, so we can plant a lot of different things. That's very awesome. You could get all small scale electronics in there with wireless communication.
On another subject, what does a limpet eat?
The same plants that are living.
I see.
And so when we maintain those, I haven't said it, but these little creatures unfortunately never made it to America. The conditions on the Boston coast would be, where it's rocky, would be perfect, but they only exist on the East Atlantic coast. They never came over. So what we're doing is we import them from collaborators in England, and then I go out here and collect the food plants here on the coast. And that's the kelp that we eat.
Okay. Well, don't release them.
I know I'm allowed to.
Okay.
I think they would be pretty.
Yeah. Who knows what they would do?
They're pretty much bottom of the food chain. everything eats the fiber. One is in our tank actually. We have little small crabs that appear over there. After 2 months after we put the last sort of outside plant in, and then we all started to get sea urchins. They all have different techniques of eating them. It's quite fascinating.
Did you get a chance to look at the, I might have missed this, but whether or not you got a chance to look at the, any of the polarization behavior when you apply the strength and stretching of the fibers?
So the fibers we haven't done yet. What we have done is we have looked a lot at the spectra. I didn't show that there. I have that in my master paper. So what we do is we scan over the fiber diameters. We use the microscopy system. We cut the light from the microscope perspective through a port in the microscope into the fiber, and the size of the fiber defines your field of view. And that means you can get lower than 1 micrometer area resolution spectroscopy. And then we looked at the reflection of the different parts of the fiber. I could probably do this with polarization as well. What was interesting there is that we essentially measure the band diagram just by scanning across the fiber. And the reason why you do that is the band diagram comes obviously the wave vector of light, or if you want the kx component in terms of microscopic propagation, and the deviation from the original incidence light. The reason why we do this is the lens, the fibers are curved, so they act a little bit like a lens. And it's very similar to putting a lens in the backfocal plane or the backfocal plane. We essentially get to convert wave vectors into position of the fibers. So brushing over is very, very flatly now. It's an interesting effect. So I think we could use this sort of same scanning technique to look at polarization. How it happens across the fiber and what happens for different deformations.
Because it may also be interesting just to see whether or not you get specific polarization isotopes out of that system.
Yeah.
Right, with strength. And then you use that for control. I mean, I know that normally the polarization will be taken from the longitudinal axis of the fiber, but you have such an unusual system here that you may get some higher results that could be.
So there is some effect in the saw, and that's fine, but you get, I guess, mostly from defects in the fiber, because when you roll it, you get some fast edits, and you get coupling to some cladding nodes where the actual light is confined to cladding, and that should have some polarization. Actually, it has some polarization, that's I modeled that, so I'll show you that. One other aspect that you mentioned, that's sending light through the fibers. We haven't shown much data on this yet, because we're still playing with that, we still don't know exactly what we're seeing, but it's really funny. We can send light through hollow core fibers, like most of the work that you're thinking, for example, and the spectrum depends obviously on the multilayer field signals, so we can change it by stretching fiber to send light through. Well, I would expect coming on the other side that we send light from a relatively wide angle of incidence, light amount aperture, is that we get separation of spectrum components radially over these fibers. We see some of that. We're now hampered by defects again of fibers. It's either the hollow core or the cladding that makes the spectrum.
I was just interested, when you started scaling up the size or the length of your fibers, were you still spin coating on 6-inch wafers, or you looked at other ways of depositing very thin, uniform films that could be wider?
So we're looking at these other ways, and one of them is we played around with plate coating. I think you have to go to people who really know what you're doing. It starts out, it's feasible, but it's not trivial. What I'm now excited by is this, what we call flow coating. It's not the standard flow coating. It's coating a film of polymer on the flowing surface bond. And so to make that flow long enough, we get the solution here. And by the time that it's down here, the solid is evaporated, and it's in the film, we can pick it up. And so that, my students make really good progress on this, so I think it's going to work. And that means that now the next problem that you have to solve is to make a film of this length. You can obviously roll this on the same fiber over again, but it's the point in making one of these same So now we have to translate the fiber